Okay, we are now recording. All right. So before I start into the good stuff, does anybody have any questions about anything in general? Life, the universe, how the class is running? Okay, I don't see any questions popping up. Okay, well, let's go ahead and jump into the good stuff then. All right, so first of all, the quiz that we took last time, hopefully you guys agreed that was a pretty easy quiz. So how about you guys tell me right now? So the number that you see on the screen here, how many sig figs? So Van is saying 4, Sky is saying, okay, so everybody's pretty much in agreement that it's 4, and I agree with that as well. So we know that these two zeros that you see over on the right there, those are just what do we call placeholders. They are very important. They serve a very important role. They serve a very important role. If those two zeros weren't there, then instead of having 302,800, we'd only have 3,028, which is a very, very different number. So those zeros serve a very important purpose, but they're not significant. Okay, all right, let's move on to the next one. Okay, now here is another number, and it's got a 0 on the right. So does that mean that it's not significant? Does that mean there's 5 sig figs, or is there 4 or what? Okay, so it looks like everybody's saying that it's 5. Okay, that's good. So if the 0 on the right wasn't significant before, why is it significant now? Well, it's because it's where it is relative to the decimal that's important. Okay, um, so this 0 that we have right there, we didn't really need it because the number 39.030 and the number 39.03, they're the same number, right? So that 0 that we put there right there, he doesn't serve any purpose as a placeholder. If he wasn't there, we'd have basically the same number. So if we put him there, that means we had a reason for putting him there, and the reason is because we know that it's significant. Okay, we know that it's not 39.031. Okay, we know that it's actually 39.030. Okay, so we're all in agreement that yes, there are 5 sig figs on that one. Okay, so move on. All right, so we got two numbers. We're going to divide them. And so without even pulling out a calculator, we can tell which one of these is the right answer because all the choices we have to choose from, they just have different sig figs in them is all. Okay, so so if we look at the two input numbers, we got a number here that has 2 sig figs and is being divided by a number that has 4 sig figs. So the rule when you're multiplying or dividing is whichever one of your input numbers has the least number of significant figures, that determines how many sig figs you're allowed on the output. So in this case, 2 is the least number of sig figs on the input. That means the output cannot have more than 2. Okay, all right, now let me warn you, this rule only applies if you're multiplying or dividing. If you're adding or subtracting, then there's a different rule, which I don't want to take the time to go into today. When you take chemistry or physics, either Coach Miller or I will explain that the rule for adding and subtracting is different. But I don't want to get into that detail right now. I want to stay focused on what we're going to do in this class is pretty much always going to be multiplying, dividing. If we ever have a case where we're going to be adding or subtracting and sig figs are important, I'll talk about it then. Okay, so question number 4. Okay, so this time we're multiplying two numbers. And when I look at the first number, I see, let's see, 1, 2, 3, 4, 5, it's got 6 sig figs. When I look at the second number, okay, some of you might say it has 4 sig figs, some of you might say it has 3 sig figs. I hope we all realize that the correct answer is 4. Okay, so then that means our answer can only have 4 sig figs in it. So we can rule out 2 of these right off the bat. The first choice and the last choice, they have too many sig figs, so we can rule them out. Okay, so then the question is which one of these the remaining 2, which one of those is the right one? So in this case, we're gonna have to pull out the calculator and put the numbers into the calculator. So when we do that, okay, so there's the number that appears on the calculator, which of course is more sig figs than we're allowed. So then we have to say, okay, now we're only allowed 4 sig figs. So what I like to do is I like to, at least in my mind, if not on paper, I like to draw a little line there. So if we're allowed 4 sig figs, then right here where you see the red line, that's where we're going to have to cut it off. But do we truncate it, which means to just get rid of those extra digits, or do we have to round? Well, and the answer is we have to round. Okay, so we don't just cut it off here. We have to look at the numbers after there, especially that 6 there. So if that number is greater than, if it's 5 or greater, that means that our last number here on the left side of the line, we're going to have to round that up. If, on the other hand, this thing was less than 5, then we'd round it down. Okay, so we're going to have to round up. So the answer then is 4.887 times 10 to the negative 14. And you guys all understand on your calculator when it says e negative 14, that's just the calculator's way of saying times 10 to the negative 14. All right, last question from the quiz. So I've got 4,290 seconds. I want to know how many hours that is. Okay, so the way that I do it, if I follow the Ames method, I take the number and I write the conversion factors in parentheses. Don't forget to cross out the units, make sure, because it's so easy to get them wrong. You know, you might do 60 minutes on top and 1 minute on the bottom. It's an easy mistake to make. But if you follow the Ames method and you cross them out, then you'll know that you've made a mistake. Okay, so the calculator gives me this big long number here. So the question is, how many sig figs am I allowed to use? So I look at this input number right here, and that 0 is just a placeholder, so it's not significant. So I've got 3 sig figs. Now, some of you might look at this 60 and say, hey, wait a minute, that 60 only has 1 sig fig, except I hope you guys all remember that this 60 here is not a measured number. It's a defined number. 1 minute is not approximately 60 seconds. 1 minute is exactly 60 seconds. So this 60 has as many sig figs in it as you want. It's got an infinite number of sig figs. So do not let these 60s, or this one here, do not let them limit you on the sig figs. So this guy right here, he's the only one that determines the sig figs. And he's got 3 sig figs. So that means our answer has to have only 3 sig figs. And so you'll notice that, so if we draw the line right here, the number to the right of the line is less than 5, so we're going to round down, not up. Okay, so I'm trusting everybody's okay with that. Are there any questions about the quiz before we move on? Not seeing any questions. Okay, so I will go ahead and move on. Now, just a reminder of something that I talked about last time. I've set Canvas on purpose so that it lets you retake the quizzes as many times as you want. So you can just go through and, you know, if you don't get a perfect score, go back and do it again, see if you can figure out which one was wrong. You know, take it as many times as you need. That's not cheating. I've done that on purpose. Okay, but you have to tell me if you go back and retake a quiz after the deadline is passed, then I may have already transferred that score into Canvas, and I do not have Canvas and SIS Aspire. Yeah, so I manually transfer the grades from Canvas to Aspire, and I do it, and it's not automatic. So if you go back and retake a quiz after the deadline is passed, you got to send me an email telling me that you've done it. Otherwise, your new higher score will not appear in Aspire. Okay. And also remember that once we've taken a midterm, then the quiz retakes are no longer allowed after that. Okay, so let's jump into the new stuff. So I didn't give you an official homework assignment over the weekend, but last week I did tell you to start reading chapter 3 in the book there. I asked you to make a list of any questions you had. So let me pause for a second. Do you have any questions? Was there anything in the reading that you thought was a little hard to understand? Okay, not seeing any questions pop up. Okay, well, let's go ahead and move into the new stuff then. Okay, so when you were in junior high school, if your junior high school science teacher did her or his job properly, then you will have learned about simple machines. And what you see here on the screen here, these are basically what most people consider to be the 6 types of simple machines. Now, some people say that these guys on the bottom here are really just a special case of the inclined plane. So like the wedge that you see here, a wedge is really just a special case of an inclined plane. And the screw that you see here, it's also a special case of the inclined plane. What we've done is we've taken the inclined plane and we've wrapped it around a cylindrical shaft. So some people argue that there's really only 4 types of basic machines. Semantics, I'm not going to worry about it. Let's go with this drawing here. Let's say that there's 6, okay? And so in the reading, they've talked about these machines, these simple types of machines. So what I want to do is I want to take a couple minutes and let's talk about them one by one. So the first one we're going to talk about is the lever here. This one's the simplest and easiest to understand. Okay, so you guys have all played on the playground when you were little kids, you know, the teeter-totter. All right, so you can get a really big kid right here, and a little tiny young child can balance the weight of the big child if the young child sits further out away from the pivot point here, which, by the way, this pivot point has a special name that begins with an F. Anybody remember what it's called? I'm going to sit here and tell somebody, okay, very good, fulcrum, okay. All right, so the pivot point is called a fulcrum. Okay, so I'm going to use those two interchangeably. All right, so if the little kid who doesn't weigh very much sits further away from the fulcrum than the big kid does, then what's going to happen is this machine, this lever, is going to multiply the force. In this case, it's the gravity force, the weight of the little kid. It's going to multiply that force in order to balance the big kid. So you guys, when you were little kids playing on the teeter-totter, you were doing physics. You may not have known it, but you were. All right, so calculating the force multiplier for a lever is really, really easy. We just take the distance that the physics book calls it DE. Now your book, the robotics book, they don't give it this name, but I'm going to use the terms that the physics book uses, because next year when you take physics, or maybe the year after, anyway, whenever you get around to taking physics, let's use the terms that you're going to use then. Okay, so DE is the distance from the fulcrum to the place where the effort force is going to be exerted. So FE stands for the effort force. That's the force that you are exerting, okay? And then over here, we have the resulting force. Or you could think of it as the output force from the machine. And that's the force that's going to be multiplied. Notice how this arrow here is bigger than the arrow here. That's one thing about vectors that I didn't mention before. When we're drawing vectors, it's a good practice to make the length of the vector represent the strength of the vector, okay, or the magnitude. So in this case, with a little bit of input force, you can produce a lot of output force, okay? So if we just take the ratio of these two distances, that will tell you the force multiplier, all right? So in this case, 7 divided by 1, obviously, so it's a multiplier of 7, okay? Now, a can opener is also a lever, is just a different kind of a lever. So right here at the very end of the can opener, that's the pivot point. So when you pull up on the can opener, it's going to pivot right around that point there. And so the distance from there to where the little hook is, that's very small. The distance from there to where you're exerting your force is very big. So the ratio of those two distances tells you the force multiplier. But when you're thinking about distances, you can also think of it in terms of how far does your hand move compared to how far the bottle cap moves. So you can see here, your hand started out down here, right? So your hand started out down here, and your hand had to move all the way up to there. So your hand moved a pretty big distance, whereas the bottle opener here, you moved a very small distance. So if you want to calculate the force multiplier, One way to do it is to calculate the distance from the pivot point to the place where the forces are being applied. But another way to do it is to calculate the distance that your hand moves divided by the distance that the business end, the end that actually does the work, okay, that it moves. And you'll find that the ratio is the same in both cases. All right, so that's a good way to calculate the force multiplier. All right, now, okay, so we know now that machines multiply your force, but they don't do it for free. You have to pay a price. All right, so you guys all hopefully remember from last week that force times distance is equal to work. Now, this is only true with the force and the thing that you're moving if they both move in the same direction. If there's an angle in between the two, then we have to use this thing called sine or cosine, but I'm not going to do that in this class. I'm going to keep it simple. And this, we're always going to say the force is pointing the same direction the thing moves, so we're not going to worry about sines or cosines. But when you take physics, then we'll do it the more correct way, the more general way. Okay, so we know the work is force times distance. Okay, so the thing about a machine is it can multiply your force, but it cannot multiply the amount of work that you do. Okay, so if you want to lift something up, and let's say that you have to do 100 joules of work to lift it up, doesn't matter whether you're doing it by hand. Let's say I've got this calculator here. I want to lift the calculator up. So let's say it takes 100 joules of work to lift it up. If I were to use a machine, it still is going to take 100 joules. The machine cannot multiply the amount of work that you do. The only thing the machine can do is multiply the amount of force, okay? So we know that work output is going to be the force output times the output distance, the distance that the whatever you're trying to move, whatever it moves. Okay, and then so on the left here we got the output force times the output distance. That's the output work. And on the right we got the input force times the input distance. That's the input work. We know they have to be the same. Okay, so if a machine multiplies your force, if it takes your input force and it makes the output force bigger, and yet the left side of the equation has to still equal the right side of the equation, the only way that can work is if the distance that it has to move is smaller. Okay, all right, so that's the price you have to pay, is that a machine will increase the amount of force, but the distance that it moves is less. So if you want that thing to move a long ways, your hand has to move a lot farther than it would had you done it without the machine. Okay, and in fact, the output work is almost always less than the input work because of friction. Pretty much any machine in the real world is going to have some friction. So let's say that I have one of the machines we're going to be talking about in just a minute is a pulley. We're going to talk about that very soon. So if I have this pulley and it's going to multiply my force here, okay, so let's say that I'm going to use this pulley to lift something, and it's going to, and 100 joules of work is required to lift the thing. If I only do 100 joules of work on this side of the pulley, because of friction inside the pulley, my output work is going to be less. Okay, so I'm actually going to have to do more than 100 joules of work. So these machines here, these wonderful things that multiply your force, yeah, the price you pay is you have to end up doing more work using a machine than you would had you not used a machine, unless you're really lucky and you got an absolutely frictionless machine. Okay. So let's look at a couple more types of machines here. So we've talked about the lever. I think it's pretty straightforward. If anybody has a question, go ahead and pop up, type it in, but I'm not seeing anything. So I'm going to assume you understand about levers. Okay, let's talk, let's talk a little bit more about the frictionless thing here. So up until now, I have called the force multiplier a force multiplier. But physicists they have a special term that they use. They like to call it the mechanical advantage. And in your book, your book uses the same term, mechanical advantage. So whenever you see mechanical advantage, that's really just a force multiplier. Okay, so the ideal mechanical advantage, that's what the force multiplier would be in the ideal case when there is no friction. So the ideal mechanical advantage is always going to be the ratio of the output force, the resulting force, divided by the input force, which is also sometimes called the effort force. So the ratio of those two. So hopefully, like let's say, remember this lever back here where we had 7 feet here and 1 feet there? Okay, so the ratio of the distances was 7 divided by 1. And so that means that the ratio of forces is going to be 7 divided by 1. So that's the ideal mechanical advantage. Okay, now the actual mechanical advantage is going to be a little bit less than that because the output force, because of friction, is going to be a little bit less than the ideal theoretical maximum. So your actual mechanical advantage, which is called an MA, now in reality, we really ought to stick an A in front there. We really ought to call it an AMA, but for some reason, that's not what the books do. Okay, so whenever you see MA, just remember that that's the actual mechanical advantage, which takes friction into account. And if you ever want to talk about the ideal mechanical advantage, make sure you stick an I in front of there. Okay, so the actual mechanical advantage is going to be the ratio of the actual output force divided by your input force. And notice this time I did not say that it's equal to the ratio of the distances because it's not going to be equal to the ratio of the distances. Whenever you're looking at the distances in order to calculate what the force multiplier is, remember, when you do that math, the number that pops out is going to be the ideal case. The actual case is going to be less. The only way that you can really know what the actual mechanical advantage is to measure the force. So measure how much input force you are doing, measure how much force comes out of the other side of the machine. That's the only way that you can know what the actual mechanical advantage is. Okay, and as we talked about last time, no machine, well, pretty much no machine is 100% efficient. The gasoline engine that we talked about last time was only like about between 20 to 35% efficient, depending on whether you got a small car or a big truck. Okay, so the actual or the efficiency is going to be the ratio of the actual mechanical advantage divided by the ideal mechanical advantage, and we usually express it in a percentage. So what we're going to do is after we divide the two, we're going to multiply by 100 because it's tradition. You don't have to put efficiency in terms of percentages, but that's the way people do it. So if you take the ratio of the actual output force divided by the ideal theoretical maximum, that's going to be your efficiency. Okay. Or another way you could do it is you could take the work, the ratio of the work, but then it gets a little more complicated. You're going to have to flip them because remember the work that you have to do is always going to be more than the ideal theoretical. So if you're going to look at the work, then you're going to have to flip it so that because the efficiency always has to be less than 100%. Efficiency can never be more than 100%. Okay. So we talked about levers. I think it's pretty clear. Now, what this lever that you see right here, it's basically just pivoting right here. This is about as close to 100% efficient as you can hope to get, okay? But not all levers are like that. Some levers look more like this. Let's say that our fulcrum here is not just the simple pivot like we had up here, but let's say that we've got this bar going through here and then there's a pin that goes through the bar, and so it pivots through there. So you can see here we're going to have a little bit of friction. So in the first case here, you can get a machine that's pretty darn close to 100%, but if you do it like this, that same lever, now there's a place where friction can come into play. So we're definitely not going to have we're not going to have 100% efficient anymore. Okay, so I think we've talked about levers enough. Let's talk about another type of machine. Let's talk about the pulley. All right, so I showed you a little pulley that I have right here. Now this is a more complicated pulley. This has a bunch of different wheels on it. Let's start with just a simple pulley. So if we look at this simple pulley here, you can see that we got a rope going down and a rope going up here. And so I wonder what the force multiplier in a case like that would be. Okay, well, tell you what, let's look at a real pulley. So hang on for a sec. So I have a pulley set up. Okay, so hello. All right, so let me switch my camera here. I'm going to switch to the rear camera rather than the front camera. Okay, so you're seeing my fireplace right now. Okay, so I'm going to swing my camera around. So we're looking out my patio window. Okay, so this is my patio. And if you look on the floor there, you can see, oh my goodness, I left my tool bag outside. Okay, I better go get my tool bag. So what I'm going to do is I'm going to go outside and I'm going to try to pick up my tool bag. Okay. All right, so there's the tool bag sitting right here. Okay, so I'm going to pick it up. Okay. Right. So, oh my goodness, there's a lot of tools inside that bag there. This bag might be pretty heavy. So here goes. A little bit. Okay. All right, so here goes. I'm going to try to pick up the tool bag. Oh, it's so heavy. Oh, I threw out my back. Oh, no, I just threw out my back. So you guys know I didn't really throw out my back. I'm just pretending. I hope I get an Oscar for the acting there. Okay, so you guys know that when you're picking up something really heavy, you don't want to pick it up like this. You want, they tell you lift with your legs, not with your back. Okay, so I've got this bag here and it's so heavy that it's kind of hard for me to lift it. So if only I had a machine that could help me lift this bag. What's this? Oh, hey, by a strange coincidence, there just happens to be a pulley hanging from the ceiling here. So how about let's do this. I'm going to take this rope. I'm going to put it through the pulley. Okay. And I'm going to use this to lift the bag. Okay. So here goes. Okay, now the bag is still pretty darn heavy. In fact, when I'm doing this right here, the force that I have to exert right now is the same force that I would have had to exert had I lifted the bag up. So let's say this bag is a 50-pound bag, right? So using this pulley right now, I still have to pull with 50 pounds in order to lift this guy up. But the advantage is that instead of having to exert an upward force, which could possibly hurt my back, I can get away doing the job with exerting a downward force. Okay, so what would the force multiplier in this case be? Well, it turns out the force multiplier would be a -1. So the magnitude of the force that I have to exert is the same as it would have been had I not used the machine, but the direction is different. And it turns out that's a very useful thing, because this way I can lift the thing without risking hurting my back. Okay, so a force multiplier of -1 turns out to be a useful thing. But what if this bag was so heavy that even with this arrangement here, it's heavier than I'm capable of lifting? Okay, so what I need is a more sophisticated pulley. If only I had a more sophisticated pulley. Oh, wait, what's this? As luck would have it, I just happen to have a more sophisticated pulley right here. Okay, so this pulley, if you look at it, you can see it's got a whole bunch of little wheels and things here. It's got multiple ropes. This is a complex pulley. The first one we saw was just a really simple pulley. Okay, so I'm going to take this more complicated pulley here, hook it onto there like that. I'm going to attach it to my tool bag. Okay, now watch the magic of physics here. Okay, so now when I pull the bag up, it is really easy to pull the bag now. Okay, so if this is a 50-pound bag, I can lift that bag using a lot less than 50 pounds. It's very easy to pull this guy up. But there's a price I have to pay. Remember how we said that the work that you do with a machine cannot be greater than the work that you do without a machine, and the price that you have to pay to get a bigger force is that the distance turns out to be less. So watch what I'm going to do. I'm going to take this rope and I'm going to pull this rope about 5 feet, and I want you to watch how far does the bag move. So the bag starts out about right here. Okay, so I'm going to pull 5 feet of rope. Okay, that was about 5 feet. Did the bag move 5 feet? No, it did not. The bag moved only 1 foot. Okay, let's do it again. Okay, so the hand moves about 5 feet, but the bag only moves 1 foot. Okay, so now here we can calculate what the ideal mechanical advantage of this machine is, because remember I said the ratio of the distances tells you what the ideal mechanical advantage is? Okay, so if I have to pull the rope 5 feet in order to get the bag to move 1 foot, the ratio of dE over dr is 5. That means the ideal mechanical advantage of this pulley is 5. So that means if this was a 100-pound bag, I could lift it using this pulley with it exerting a force that is only 1/5 of that, which is 20 pounds. Okay, so I hope that's clear how that works. Okay, so let me let it down here, and let me come back in. Now, if you guys have had any questions there, I obviously haven't been able to see your comments, so let me come back inside here, and okay, give me a sec to put the computer back into its regular mode here. Okay, all right, we're back with me again now. Sorry you have to look at my face. Okay, so you'd recognize that link anywhere? Okay, bro, ain't nobody falling for your too quick roll. Okay, a lot of interesting comments were typed in here while I was out there. Okay, so hang on while I get back here to. Okay. Okay. And oh, the comments disappeared again. I hate it when it does. Let me see if I can get those comments back. It did it to me the other day too. When I change my camera settings, the chat window goes away, and I can't get the chat window back. How did I get this back last time? So I can't see your comments anymore. Okay, tell you what, let's try this. Okay. Sorry for a second. I don't know why the comments window is being weird. Okay, so tell you what I'm going to do. I'm going to go back to share my screen. Okay, so I can't see your comments, guys. I'm going to have to figure out why not. So I'm just going to go ahead and I'll come back and check for comments a little later. Okay, so if you have a very simple pulley like you see right here, then notice that I've just got one wheel and I've got a rope. Okay, so this is like that first pulley that I showed you. Okay, sorry. Okay, I just got the comment window back. Okay, good. All right. Okay, so with this very simple pulley, you can see that what's happening here is that the force multiplier is -1 because my input force is downward, the resulting output force is upward, so so the direction has changed, so we call that a -1, but the magnitude of the two is the same. But if I have a more sophisticated pulley, like one of the ones that's shown here, where I have multiple wheels and multiple ropes, okay, then the force multiplier can be greater than just a 1 or greater than a -1. So in this case right here, this is kind of similar to the pulley that I just showed you, except doesn't have quite as many ropes. So I got one rope right here, comes up, goes around this wheel, down around this wheel, and back up to here. So a little hook here, that's where I would hook up my, tool bag, okay? The way to know the ideal mechanical advantage of a pulley like this is just count the ropes, okay? So if I draw a little box around the pulley that's going to be connected to the tool bag or whatever it is I'm trying to lift, okay? Just draw a box around here and you'll see that there's two ropes. There's one rope coming in here, going around there and coming out there. Now, some of you might argue it's the same rope, but if you just look at it, you see there's one here, one there, okay? So the tension in the rope is always going to be the same if it's a frictionless pulley. And so what we've got is we've got two ropes pulling up as opposed to only one going down. So the ideal mechanical advantage of this one is going to be 2. So actually it's going to be -2 because the downward force here is going to result in an upward force there. So my mechanical advantage here is a -2. So I can lift a 100-pound tool bag by exerting only 50 pounds of force if it's frictionless. If there is friction, then I'm going to have to do a little bit more than that. Okay, if I do a pulley system like this, so it looks like it's the same pulley, but you can see what happens here is the rope comes around here, around there, and when it goes up here, it goes around the wheel again and comes down here. So if you count the ropes here, then you get 3 ropes. So the mechanical advantage now becomes 3, actually -3. Okay. Hey, John, I'm seeing your comment now, and I don't understand what you're saying. Does the server I will? I have no idea what you're asking there. Can you maybe rephrase your question? Okay, so if I come over here, you can see I've got now, over here it's kind of hard to see, but there's actually 2 ropes here. So I got a total of 4 ropes. So my mechanical advantage advantage now is going to be -4. Come over here, now it's -5. Come over here, now it's -6. Okay, so you can see that with a pulley system, just by counting the ropes, you can know what the ideal mechanical advantage is. Now the actual mechanical advantage, that's going to be different because these pulley systems here, they have friction. Okay, so like here is one of the things like you see in the picture there. You can see we've got there are lots of different wheels all together on the same block. So this is called a block and tackle. There's a lot of friction in those wheels there. So let's say that I've got a case like over here on the right. I've got a thing where my ideal mechanical advantage here I said was 6. My actual mechanical advantage because of friction is actually going to be something less than that. Okay, so how can I know what the actual mechanical advantage is? Well, the only way is just measure. So I exert some input force and I measure what it is, and then I go over and I measure the output force to see what it is. That's the only way to know what the actual mechanical advantage is just measure the forces and see. Because friction's a little bit complicated to calculate. So that's pulleys. Does anybody have any question about pulleys and how pulleys work? Are you guys still there? Some of these comments you've been typing in the box there make me wonder if you guys are still awake, if you're still paying attention. So is anybody else? So can you hear me? Let's do another mic check. Can you guys hear me? Okay, good. You can hear me. Okay, so no questions? All right. So we've talked about, okay, good. No questions. All right, glad to see that. Okay, so we've talked about levers, which are pretty much the easiest possible machine to understand. We talked about pulleys, which are a little bit more complicated, but not too much. Oh, Marshall has a question. Okay, go ahead and ask it. If you want to turn on your mic and ask it verbally, that's okay. So what's your question there, Marshall? If you hold down your space bar, you can just speak it. Okay, thanks. All right, so hey guys, let's focus here, okay? All right, so I'm going to ignore that question there, Marshall. We really need to focus. Okay, so another type of machine here is the inclined plane. All right, so inclined planes I think are pretty straightforward. So if you've got a box here and the box is on the ground and you need to get the box up to some table or something like that, you know, the box starts out down here, you want to lift it up to there, but the box is too heavy. All right, so well, you could use a pulley or you could use a lever, but how about an inclined plane? So let's say the box starts out down here and you want to get it up there. So you're going to slide the box over here, put it on the inclined plane, push it on here. And so the inclined plane is going to support some and maybe even most of the weight of the box. So you don't have to worry about supporting the weight of the box. You just need to push it up the ramp here. And it turns out that you can push it up the ramp using less force than you would have had to use had you lifted the box straight up. And so if you want to know what the ideal mechanical advantage of the ramp is, just take the ratio of the distances. So look over here. So this is the distance, the vertical distance. Let's just focus on the vertical distance. So the vertical distance that you would have had to lift the box here is 3 feet, okay? But because you use the ramp here, let's say that this ramp is 5 feet long and it's pushed at just the right angle here. So instead of pushing at 5 feet, you had to push it, or instead of pushing at 3 feet, you had to push it 5. Hey, John, what's with this YouTube thing that you keep trying to get us to watch here? You've posted this link a couple times here. What is that a link to? Is it relevant to the class? Okay, well, if it's not relevant to the class, please don't post it, okay? Guys, let's focus, okay? All right, so, so if you end up having to push the box 5 feet in order to do the job that you could have done in 3 feet had you not used the machine, just take the ratio of those two. So take 5 divided by 3, and that will tell you what your ideal mechanical advantage is, okay? So remember, the ratio of the distances, that's always your ideal mechanical advantage. Okay, so in this case, the ratio is 5 over 3, which works out to be 1.7. So that means that you can get away with using 1.7 less, you can take 1 over 1.7 as the ratio. That's what your input force will be. So your output force, so you can lift something then using a ramp that is 1.7 times heavier than you could have used had you not used the machine. And so Luke is saying, yeah, if you know trig and you know sines and cosines, you could figure that out. That's correct. Okay, so there are a couple other types of machines here, but I don't want to take the time to talk about them. Your book, I think, does a reasonably good job of talking about them. So I just kind of gave you a little introduction right here. So what I want you guys to do is I want you to finish reading the book, or at least chapter 3, not the entire book. But so you have an official homework assignment now. So by the time we meet again on Wednesday, I want everybody to have read all of chapter 3. Okay. Now, those of you that have already looked at chapter 3, you'll notice at the end of the chapter they have a couple little questions. Normally what I would do is I would say answer the questions at the end of the chapter, but I don't think those are particularly useful questions. So what I'm going to say is don't worry about answering the questions at the end of the chapter. What I am going to do is I'm going to post some questions on today's quiz, because you know that's how I measure attendance, is with the quiz. So I'm going to put a couple questions in today's quiz that are based on what we've talked about. And so those are the questions that I want you to answer before Wednesday. And so if you just remember what we've talked about now, like these equations right here, these are going to come in very handy on the quiz. So if you want to know what is the ideal theoretical best force multiplier that you can hope for, okay, in the ideal world where there's no friction, okay, just look at the distances. Take the ratio of the distances. So if it's a lever, these are the distances from the fulcrum to wherever you're applying the force. Or this could be the ratio of the distance that your hand moves compared to the distance that the tool bag moves. It works both ways. But remember, if you take the ratio of the distances, that's always going to be the ideal theoretical best possible. The actual is always going to be less than that if there's friction, which there pretty much always is. And then efficiency is just going to be given by the equations that you see right here. So in the one or more of the quiz questions might ask you to calculate the efficiency given the various types of input, the numbers that I give you. So this page right here, you might want to copy these down and have it with you while you're taking the quiz. That's pretty much it, I guess. Okay, so we covered a lot of material there pretty quickly. I think the book does a pretty good job of understanding it. So if you didn't fully understand everything that I said, the book does a good job of explaining it, is what I meant to say. So if you didn't fully understand everything that I just said, you go through, read the book, it does a pretty good job. Or here's the advantage to having recorded videos. Go back and watch the video again. If it didn't really sink in the first time, watch it a second time, and hopefully it'll sink in more there. Okay, so are there any questions before I end the recording? Not seeing any questions. Okay. Okay, so I'm not seeing any meaningful questions. Okay, well in that case, I will go ahead and stop the recording. Well, actually, I guess I should do it officially. Going once. Okay. All right, here we go. All right, going once. Going twice. No questions? Okay, sold.